Good afternoon, folks. Sorry, little technical difficulties. I'm Rohini. I'm in charge of the PIC team at Yahoo, and this is Daniel. He is in charge of the PIC team at Hortonworks. Today, we are here to talk about PIG on Taze and the work we have been doing for the past 3 quarters to speed up ETL with PIG. So the agenda is I'm just going to introduce about the team. Then there'll be a short intro on PIG for those of you who are not familiar with PIG. And we're going to talk about why we decided to go with PIG on Taze, and then a deep dive on PIG on Taze. So here is a team. Making a special mention of the team because the model with which we worked on this project is very different. It is a cross-company collaboration. We have folks from Hortonworks, Yahoo, Netflix, and LinkedIn contributing to the project, which was a very organized project. We had sprints. We met every 3 weeks. We had bi-weekly calls. We had time allocated, committed from each of the company, and we accomplished a lot in 2 quarters. We got it like 95% feature complete in 2 quarters. In fact, Mark and Chialsu gave a talk on this in ApacheCon on like how this model worked. So we put a special slide for the team. This is Daniel. He's kind of the architect for the project and is a subject matter expert who knows everything about PIG. Then there's me. Then there's Chialsu from Netflix. Then there's Olga. She's my manager. She's put together the team. She no longer codes, but I wish she does. Then we have Mark and Alex from LinkedIn. I think the whole team is here today. I'll just switch it over to Daniel to talk about
Thank you.
PIG. Yeah.
So 1 minute introduction to what is PIG. So PIG consists of Okay. Sorry. So 1 minute introduction to what is PIG. So PIG consists of 2 parts, PIG Latin language and its runtime engine. So PIG Latin is a procedure scripting language. Compared to SQL, it is even closer to relational algebra, so many programs like it. It is heavily used for ETL tasks on top of Hadoop. And our motto is PIG eats everything. So even if your data doesn't have a schema, PIG can still process it. And PIG is feature rich. It has several features that standard SQL doesn't have. So here is a list. I don't want to go into details. And the PIG users. So PIG is heavily used for ETL tasks by many internet companies. So at Yahoo, 60% of total Hadoop job is running PIG. And every month, there are 12 million PIG jobs submitted. Other heavy users of PIG include Twitter, Netflix, LinkedIn, eBay, Salesforce, and more. And PIG is a standard data science tool. It is covered in textbook, in university textbook of data science.
Okay. I'm going to talk about why we went with PIG on Taze. So PIG currently uses MapReduce as the execution engine for its backend. But we had to move away from MapReduce because it has its limits. So PIG with the query plan is essentially, the query plan is a DAG. So since the MapReduce is just, a job can just have a map phase and a reduce phase, we were limited to jobs and we had to store the data and intermediate output and then like launch a sequence of jobs to get the same whole PIG script run. So having a DAG execution framework was essential for us because it fitted very well, went very well with the query plan. So that's why we wanted to move to Taze. And why Taze? So there are other DAG execution frameworks available there, but why did we go with Taze? So we did evaluate others, but we went with Taze because it's a low-level DAG framework. So it allows us to specify the individual vertices, what process runs inside each vertex, and how to connect the vertex, how to schedule the vertex, and even how to route data between the vertices. So we wanted this customization and flexibility. This allows us to write efficient algorithms and do better planning. So since Taze is highly customizable with like every part of it where you can plug in implementations of your own, this was something very exciting for us. I'll talk more about what are the features we have used and cover it in later slides. But this is one of the main reasons we went with pig on Thais. The other main reason is resource efficiency. At Yahoo, cluster utilization is a bigger problem for us. We have millions of jobs running and it's always competing for resources. Some jobs, even though they're like, they can run fast, they are like, backlogged because you don't get resources. Having to cut down on the resource utilization, both CPU and memory, is very important for us. With better DAGs and with better execution plans, eliminating a lot of stages without having to store data in intermediate stages, Thais gives us a lot of resource efficiency. And of course, performance. We want performance, that's one of the main goals. And we were able to achieve performance without having to throw memory at it. So with existing memory and with existing resources, even actually using less resources, we are able to achieve better performance. So this is one of the another key reasons that we went with pig on Thais. It's natively built on top of Yarn. At Yahoo, we have been running Yarn in production for past 2 years. So we have all the environment set up, and this fits very well into our plan of being investing in Yarn and having our frameworks run on Yarn. And multi-tenancy is very important for us because internally, even though it's a single company, we have lots of users. We have different properties, Flickr, mail, search, everything. They're all different customers to us, and a lot of different teams like reporting, analytics. All of them use Hadoop and we treat them as our customers. So multi-tenancy is very important for us. And all of that come for free with Yarn. Thais is natively built on the ground up on Yarn. So that is another key thing for us. Scale. So Yahoo, all of you would have heard a lot of times by now that Yahoo runs at like a huge scale, Hadoop at huge scale. We have around 24 clusters with like around 30K plus nodes. And there are clusters, very big clusters, which are like 4K nodes and all that. So we wanted something that will scale and run on those clusters, which will run hundreds of thousands of jobs per day and millions of tasks, which will translate to millions of tasks. We wanted something that scales to that. So we wanted something that doesn't just like run well on a 100 node cluster or 200 node cluster with more memory, but something that runs on this kind of environment. We even wanted to scale more to like 5,000 nodes, 6,000 nodes. So scale is also a very important thing for us. Security is another key factor. So we rely on Hadoop security, the Kerberos security and delegation token mechanism. Thais has that built from the ground up. And the other reason is that we get excellent support from the Thais community. If those folks are here, thank you guys. Vikas, Siddharth, and Hitesh. It's kind of like a personalized support because every issue we report like, kind of gets fixed in a day or two. And having Daniel sit next to them kind of helps. Yeah, okay. Pig on Thais, I'll let Daniel continue on the design and implementation aspects.
So this is a diagram of pig from a high-level design. So when user submit a pig query, it first will translate into shared logical plane and physical plane. And depends on the execution mode the user supplied in the command line, it will send to either the MapReduce engine or Thais engine for further processing. So in this picture, we can see Thais engine is in the same position of MapReduce engine. So we don't translate MapReduce plan into Thais plan to implement Thais. Both Thais engine and the MapReduce engine are the first-class citizen of pig. This multiple backend architecture is extensible. So if someone wants to implement another backend for pig, they can follow the same pattern. So this is a typical pig script showing both MapReduce plan and Thais plan. The left side showing the MapReduce plan. So in this MapReduce plan, we have two MapReduce jobs. The first MapReduce job uses a technique called multi-query optimization, which will multiplex the input to simulate a split. So in the reduce side, we can group by different keys in the single stage simultaneously. And after that, we will dump the intermediate file to HDFS. And the second MapReduce job will load the intermediate data from HDFS and do the join. And let's see the right side, which is the Thais plan. So we load the data from HDFS and send to multiple output vertices. So every output vertex will group by its own key, and finally send to the join node to do join. Compared to MapReduce plan, test plan have several advantages. First, in the MapReduce plan, we have MapReduce, altogether 4 stages. And in test plan, we have 3 stages, thanks for the MapReduce reduce pattern test provides. And second, in the MapReduce plan, we will need to dump the intermediate files into HDFS and load again. And that was eliminated in the test plan. So that's a significant reduce of the I/O cost. And third, if you look at the test plan, it is much closer to the pig script user actually write. So for developers, it's much easier to reasoning and debugging. So let's skip this. The next slide shows how pig doing the distributed out by. So I don't want to go explain the DAG in detail, but just want to bring out the advantage of test plan over the MapReduce plan. So first, it has less stages than MapReduce plan. So in the MapReduce plan, we have 3 MapReduce jobs. And the first MapReduce job is the map-only job. So it's altogether 5 stages. And in test, we have 4 stages. And also, we have we don't have the intermediate files in test plan compared to MapReduce plan. And third, in test plan, we can specify the edge semantics to test to tell test that one of the edge is actually one-to-one unsorted edge. So test runtime engine can schedule these 2 vertices to run in the same container, and the import data don't have to be sorted. So we save time on sorting those import data. And the fourth, in MapReduce plan, we already did some optimization. So we will distribute the sample file through distributed cache. But still, for every container, they will need to load data from distributed cache and then save into memory. And in test, we will load the data once and save it in memory, and we'll cache it. So if the next container, if we use the container reuse, then the next container will find those samples in the memory itself. So it don't need to load it again. So Pig also use several low latency features of test, which include the session reuse and container reuse. So when you submit multiple MapReduce jobs to Yang, we will need to create AM for every MapReduce job. And when the MapReduce job finish, we will shut down the session. We will shut down the AM. And for test, when we submit the DAG, we still need the AM to manage the DAG. But when the DAG finish, we don't shut down the AM immediately. Instead, we put it into a session pool managed by Pig. So whenever possible, Pig will reuse the AM and without creating a separate new AM. And also container reuse. So container reuse is a feature provided by test, which is turned on default by all the Pig script. So when user launch the Pig script, whenever the resource specification is compatible, test will reuse the container. So the benefit is significant. We will avoid the overhead to relaunch the JVM and localize the resource. And we don't need to release the container and then compete for the new container again. So when the resource congestion happens, this will be a huge save. Next, I'll hand over to Rohini to talk about additional features.
Okay. So earlier I was telling that everything in Thales is customizable and we have put a lot of our own implementations. So this is a few example of what we have done. So if you assume like map reduce, you have map phase and a reduce phase. So that would translate to a map vertex and a reduce vertex in Thales. So each vertex has its own processor. So if you think in terms of map reduce, a map vertex has a map processor and a reduce vertex has a reduce processor. So map vertex would, map processor would do whatever like the map phase, map runner in Hadoop does, and the reduce would, processor would be doing what the reduce task does in the map reduce. So for us, it's actually we don't need the map processor, reduce processor. So we replace them with our own custom pig processor, which just does what pig needs, and we eliminated a lot of overhead there. And then custom input and output. So between like between multiple stages in the job, between different vertices, you pass data through it. So the way you send data, you can define your own input and output. So take traditional map reduce. Between map and reduce, you always sort the data, shuffle it, and send it to the reducer. So it's always partitioned, sorted, shuffled output. But you actually don't need that in many of the cases. You can, there are other places where we use unsorted output without partitioner, unsorted output with partitioner. So some of these cases, when we union the data, we actually don't have to sort the output. So that's one case. And when we do order by join and all that, also we use unsorted input output without partitioning. So this avoiding the sort overhead has helped us speed up things a lot. And we use a custom vertex manager for automatic parallelism estimation. So to determine parallelism at runtime based on the data flowing through different stages and setting parallelism automatically in the lower stages, we have written our own vertex manager, which determines looking at the data flow and deciding, okay, this vertex is doing a join, so the data is going to explode. So the next stage, I'll increase the parallelism. So this vertex is doing a flatten, or it's doing a filter, so let me reduce the parallelism. So all these we are able to do by, when it's during runtime, we are changing the parallelism as the data flows. So this is one of the things that we really like about it. Benefits, as I said, there's no framework restrictions like MR. We are able to change a lot of stuff, and that's made us do efficient processing and do better algorithms. Now I'm going to tell about like how we optimized map side joins, which we call replicate join in pig. So map side join is where you take a big table, you load them in different map tasks, but the small table, you load it into memory, the whole table into memory in each of the map tasks, and then you do a join. So what we used to do in MapReduce is that to ship the small table to all the tasks, we used to put it into distributed cache and then ship it. So distributed cache had its own problems. So localization of the distributed cache used to be done by the node manager. So the node manager, each node manager had, I think, a limit of 10 or 20 files that it would localize at a time. So that overhead was there. I mean, it was like blocked by that. If there are other tasks having more resources to localize, this might get slowed. And if you have more than 500 MB and 1 gig, so the node it can crash the node manager if you have like very big files that you want to put in distributed cache. So we ended up putting limits on the map side join, saying, okay, you cannot load a small table which is more than 1 gig. So all that restrictions will go away with broadcast stage. I'll talk about it. So broadcast stage is basically like you have a vertex and you have other vertex. So you load the small table in one vertex, and then the whole table you are going to send it to all the tasks in the next vertex. That's broadcasting. So Thales has this feature, and with broadcast stage we are sending a small table. And next is like object caching. So since we are reusing containers, as Daniel mentioned earlier, so once we load the small table into memory, we just keep it there. We don't like get rid of it. So if this another task from the same vertex runs on it, we just reuse this table. So we don't construct it again. So since we don't construct it again, for the second task, we don't even have to go fetch the small table from the previous vertex. So we don't fetch the input again also. So this all leads to a lot of savings. So replicate join or map side join is like highly efficient with this. And it also removes the restriction on how much, the size on which you can do a map side join. Vertex groups, this is another feature that Tasteworks put in for us, specifically to handle unions. So when you do a union, what you want to do is there are two vertices, and then you have a third vertex where you want to send the data, but you want to like combine the output of that and send it as one input to the third vertex. So they added something called vertex groups and encapsulated the output and made it appear as a single input to the third vertex. So we don't have an additional vertex which will just union both and then pass it on to the next stage. So elimination of an additional vertex to do the operation also like gave huge performance. So replicated join and union are highly optimized as of now with this. Over to Daniel to talk about dynamic parallelism.
So in pig script, you can specify the parallelism of each operators inside pig script. But it is usually very hard to determine a good parallelism beforehand. So in MapReduce, we will estimate the parallelism of the reduce using the input size of the MapReduce job. In TAS, the submission unit is the whole DAG. So it is not wise to estimate the parallelism of each vertex inside this DAG, just using the input data size of the root vertex. So TAS provide to solve this problem. TAS provide a vertex manager plugin to solve this problem. So we can write custom code to change the number of parallelism at the runtime. So in Pig, we use two types of vertex manager plugin. One is the stock shuffle vertex manager plugin, and the other one is partition defined vertex manager. So shuffle vertex manager plugin is used by group, co-group, hash, and all the other vertex which use the scatter gather edge. And so in this diagram, we show an example. So the join vertex at the runtime will find out the estimated input data size of the vertex is approximately 2 gigabytes, and the original estimation for parallelism is not appropriate if our custom policy is 1 parallelism for 1 gigabyte of input. So we need to reduce the number of parallelism at the runtime. So the problem is the input vertex is already started. We already partitioned the input data into 4 pieces. And at the runtime, when we decide to eliminate 2 tasks of this vertex, we need to reroute the input partitions. So in the vertex manager, we need to provide this routing table so TAS know how to properly reroute the input partitions to the new number of tasks. And partition-defined vertex manager is used by order by and skew join. So in this scenario, we will, when we send the samples to the sample aggregation job, we will pitch back the stats of the input. And with this information, the sample aggregation job will calculate the number of parallelism and send the number of parallelism to the partitioning job, and also in the same time, send the event to the sort vertex about the number of parallelism. And note at this moment, the partitional vertex is not started yet. So we can partition the output into the right number of partitions. With this arrangement, we don't need to reload the input data. The number of partitions and the number of parallelism of the sorting job are the same. So let's switch to performance. Let's Rohini talk about performance.
So I have some performance numbers from Yahoo and Netflix. So we didn't spend time running TPCDS or TPCH. One reason is we were short of resources, the other and short of time as well. And we wanted to work on the production scripts directly because that's where, which is what is more critical to us, and that is what like the user is going to see. So we started work directly with production scripts, analyzing production scripts and running it with Taste. So we did see like good improvements in the range of 1.5 to 3x. So I just took a sample of some jobs. So the first script is just one MapReduce job. There's actually no DAG. But since the way we optimized, it was a job with unions and a group by. Since the union was highly optimized, it gave like 1.5x performance. The second is like a DAG of jobs, but still there was lesser number of jobs. Still you get 2x because of the efficient, better planning. The third one is just to show at scale, like, it runs on large data with more tasks. You might be wondering why I have like a number which is say 74 versus 72 minutes, which is like what's there. So the reason I have that there is to say that it runs on scale. So if you actually see the number of tasks, it runs on like 25 terabyte and it's 101K tasks. So these, we have like one data set which is like often run by people, and it's like a daily data set is about 10 terabyte and people run weekly and all that on it. So for us, like able to run so many tasks is very important. So that's why I had this run, and even the Taste folks didn't expect it, and it went through fine. So there are issues. We identified a couple of issues. The Taste folks are working on fixing it so that we expect to see more performance with it. With that container reuse so many times, we should actually be seeing a lot good numbers here. But because the application manager was like, still to be tuned to handle that number of tasks, we weren't seeing performance. But still it was like slightly better than MR. And it finished, so great. Performance numbers from Netflix. Chalsu ran on the Netflix production jobs, and we were consistently seeing like 2x to 2.5x. So the Netflix folks also had Lipstick. I'm not sure how many of you have heard of Lipstick. Lipstick on Pig. Okay, many. So Lipstick is basically a tool which does visualization of the Pig script as DAG. And they had it working on MapReduce, so they got it working on Taze as well. So the Taze jobs also can now be visualized. So these are the previous, so these Pig scripts, here are their visualizations. So thank you, Netflix guys. And I'll let Daniel talk on some performance numbers on interactive query.
So besides for the heavy-duty ETL jobs Rohini just talked about, we also tested for a small data set to test the low latency feature of TAS. So here we pick a query of TPCH and run against different input size. So when the input data size is relatively big, we will see the performance, the speed up similar to the heavy-duty ETL jobs Rohini just mentioned. And when the input data size becoming smaller, in MapReduce job, the latency will dominate. So we will see higher speed up when the input data size becoming small. And another test we did for Pig test is the iterative algorithms. So we can implement iterative algorithms using by embedding Pig into scripting languages such as Python. So it basically runs the same Pig script again and again using different parameters. And in this scenario, it is an ideal case for the container reuse. So I just pick up one of the source code of my blog post 2 years ago about to implement the k-means algorithms. And without changing a single line of code, we achieve a very good number of speed up. So after the first iteration, every additional iteration will take about 1.5 seconds versus 27 seconds for MapReduce. So for machine learning algorithm, this is a huge boost. And let's skip this. And so where are we? 90% of feature, we are now 90% of feature compatibility with pig on MR. So the big missing is the test local mode, which is still an ongoing project. And we haven't implemented some real-used operators, such as MapReduce, a native operator, and collected co-group. And 98% of total 1,300 end-to-end tests, original end-to-end test pass. So the failed one mostly are due to the missing operators, and the rest of them are also properly investigated. And we also, in the process to migrate unit test to test, we already migrate most of the mini cluster unit test, but still, for the test local mode, we haven't migrated because the missing feature of test local mode. And we already merged the test branch into trunk. So if you want to play with test, you can just check out pig trunk and play with it. And pig on test will be part of pig 0.14 release. And like Rohini just mentioned, Netflix already make lipstick working with pig on test. So thanks for Jacob and Chansu. So the user impact. So there is almost no user impact for to use pig on test. The only thing you need to change is in the command line, you say -x test to tell the pig to use test engine. So you can reuse your old pig script, use a load func, store func, UDF, input format, output format, partitioner, and even most of the MapReduce properties. And the deployment is also very easy because both test and pig is just the client libraries. So it's zero-pin deployment. So I hand over to Rohini for the next step for pig on test.
I think we're out of time, so let me quickly run through it. So we are waiting on a TASE local mode support. Based on that, we'll add the local mode support. Then have complete unit tests ported, and we're working on improving stability, usability, debuggability. We have done a lot of stuff on that already, like still need some more minor tweaks. Planning an Apache release by September 2014. And we're planning to deploy it in Yahoo Research like early Q3 and get it into production in Yahoo and Netflix by late Q3, early Q4. And sorry, I missed LinkedIn here. They'll also be going with it to production soon by end of this year. We want to, like a lot of performance, we have identified a lot of things to do, but due to resource constraint, we are just focusing first on like having everything stable and everything working perfectly. So we are going to start work on performance again, getting the performance to like 5x range before we get it into production. So some TASE features are work in progress on which we have blocked. Currently there's no TASE UI, so you have to scrape through the AM logs to see what is actually happening. So the TASE team is like working on the UI, and we are hoping to get it like delivered within the next 1 month. And then there's a TASE local mode I talked about. This also is like due in another 1 week, I guess. TASE AM recovery is also in works. It actually works, but then it still has a lot of things to be ironed out. Folks are working on that. And the other thing that we are waiting on is like some input fetch optimizations. They're writing a custom shuffle handler so that data fetch between vertices is more optimized instead of using the shuffle handler that the MapReduce uses. So this is, I mean, we need this to improve the performance further. And what we are going to do with Pig to improve performance is like more new features in like TASE, which we are going to use something called shared edges, where you write the output once, but you need to send it to multiple vertices. So right now we write it multiple times and then send it to multiple vertices, waiting on the TASE feature to write once and then send it to multiple vertices. Then have multiple vertex caching. If you have the same table being joined with different things and different stages. We want to like cache it once and use it for different vertices. And we want to work on, we have replicated and join and union. Yeah. Optimize, now we have to work on skewed join, order by, and group by and join, which are the other major operators. So we are going to work on that, optimizing that. That's it. We are hiring especially for pig on Thais. So interested folks, please reach out to us. After this, we have work on pig on vectorizing pig. So if you're interested, get in touch with us. Thank you. Questions?
Questions?